What is atomic mass and molecular mass and formula mass? What's the difference? And furthermore, what about atomic weight and molecular weight and formula weight? Well, right now we're talking about masses at the atomic scale, masses of atomic-sized particles. So protons, neutrons, electrons, atoms, molecules. What we've learned is that currently, even today, we aren't able to directly measure weights or masses of atomic-sized particles. So we can't sort of pick up a single silicon atom and put it on a nano-sized scale. But what we are able to do is determine relative masses between atomic-sized particles. So this atom weighs 6 times more than this atom. This molecule is a fifth of the mass of this molecule or this atom. And so what's done is a new unit is created, a unit of mass for atomic-sized particles, with this unit based on a specific atomic-sized particle, the carbon-12 isotope, to where this new mass unit called the atomic mass unit, the AMU, is defined to be 1/12 the mass of a carbon-12 isotope, or a carbon-12 isotope weighs 12 AMU. And so with that, any masses of any atomic-sized particles reported in AMU are ultimately relative to the carbon-12 isotope. Now, it's not that the unit AMU can't be used for any matter other than atomic-sized particles. No, it's just a mass unit like any other mass unit. You can report the mass of anything you want in AMU, a baseball, a vehicle, but it's going to typically be used for atomic-sized particles, whereas something like tons would be used for vehicles, buildings, and something like kilograms or pounds mass might be used for a baseball, a table, a sofa. Something like grams would be used to measure the masses of powders, etc. Okay, and we've talked about how a link, a bridge between counts and masses in the atomic-sized world and counts and masses in the macro-sized human world was established using the mole, Avogadro's number, which is the count of the total number of carbon-12 atoms in 12 grams of carbon-12. With the mole, or Avogadro's number, we have this direct link, this bridge between the atomic-sized world and the human-sized world. Avogadro's number is how we get the conversion factor between AMU and grams. 1 AMU is equal to how many grams? And so now, but what we talked about was that the mole, or Avogadro's number, is defined in such a way to create as smooth of a link or a bridge to the atomic-sized world of masses and counts as possible. So with the AMU being defined as 1/12 the mass of a carbon-12 atom, or a carbon-12 atom is equal to 12 AMU, the mole is defined also based on the carbon-12 isotope. So we're counting carbon-12 isotope atoms, but also in 12 grams of carbon-12. We use 12 grams. And because of the way this is defined, the result is that if you determine the mass of anything you want, anything that you're defining to be an elementary entity, so anything, an egg, a proton, an atom, a book, a vehicle, a molecule, whatever you're saying, okay, here's this one item here, this one entity. If you determine the mass of that entity in AMU of absolutely anything, if you determine the mass of that anything in AMU, then that quantity, whatever the quantity of that mass is, the number, is also going to be equal to the molar mass of that something, that entity, with the molar mass being this other property. It's not the mass of the egg or the proton or the molecule. You have the mass in AMU, let's say it's 15 AMU, but it's also going to be the case, because of the way the mole is defined relative to the definition of the AMU, it's also going to be the case that elementary entity is going to have a molar mass that's equal to this quantity. So the molar mass of that entity is going to be 15, and specifically grams per mole. So the property molar mass doesn't have to be in grams. The molar mass of something, some elementary entity, all it is it's the total mass of that entity. If I wanted to know the molar mass of a baseball, well, it's saying, okay, how many baseballs do I need to accumulate? How much baseballs? So I'm accumulating more and more baseballs, and it's more and more mass. Okay, and this mass unit can be whatever you want, tons of baseballs. How many tons of baseballs do I need to accumulate to where I get to the point where I know I have a mole of baseballs, 6.022 times 10 to the 23rd baseballs. That's the molar mass, right? So again, it can be, this property molar mass can be in whatever mass unit you want. However, for the case of molar mass being equal to the quantity value in AMU of the baseball or the proton of that elementary entity, then the units of molar mass in that case are grams per mole. So if I was reporting molar mass in tons per mole, then the quantity would be equal to the mass in AMU. Okay, but now I've been using baseballs and books and vehicles as examples just to illustrate the concept of molar mass. However, when using moles as a scaling factor for counts, when using molar mass, this is done with atomic-sized particles. That's the whole reason the mole was invented. Why else would you need a count of the order of 10 to the 23rd other than for dealing with atomic-sized particles? Okay, and so the terms atomic mass, molecular mass, and formula mass, as well as atomic weight, molecular weight, and formula weight, are just referring to the masses of different types of atomic-sized particles. That's it. That is it. Now, but the term weight instead of mass is sometimes used in reference to a mass that's based on the averaging of the masses of the isotopes of a certain element, which we'll talk about in a second. However, as the textbook indicated, it's not a strict requirement for you to only use the term weight when referring to an averaging of the weights of isotopes, and then make sure to use the word mass when referring to a circumstance of specific isotopes. In general, you can use either one of these terms you want, whether or not the context is a specific isotope or the averaging of isotopes. You can say atomic mass or atomic weight or molecular mass, molecular weight, formula mass, formula weight, in whatever context you want. It doesn't matter. They both mean the same thing. Okay, but what this averaging of isotopes is referring to, which again, some textbooks might want to make this clear distinction between using the term mass or weight. So the distinction is between, okay, these masses shown here for the elements in the periodic table. You can see it's referred to, in this case, as atomic weight. These masses are based on the averaging of the masses of the isotopes of these elements. Okay, and what this is referring to is in naturally occurring substances. It could be elemental substances like elemental carbon, elemental sulfur, or it could be compounds that contain different types of elements. In naturally occurring substances, the different isotopes of the elements are going to be mixed in, with the percent abundance of how much the different isotopes are mixed in, just dependent on the specific element. Some elements might be dominated by a specific isotope. Other elements, it might be more of an even distribution between isotopes. And so because of this, if you're going to calculate weights, masses of atoms associated with naturally occurring substances, which the vast majority of the time, that's what we're dealing with in chemistry, right? Then if you're summing the masses atom by atom, you're going to use this value, which is based on the weighted average of the atomic masses of the different isotopes of that element. That way you can account for the masses of the different isotopes. And again, some textbooks, if you're ever calculating masses of atomic-sized particles based on this averaging of the isotopes, then they would prefer to use the term weight instead of mass. But the textbook we're going through indicates that you don't have to make this distinction. You can use mass or weight for whatever context you want. It doesn't matter. Okay, so, but what exactly is the difference between atomic mass and atomic weight, molecular mass and molecular weight, formula mass and formula weight? Again, these are just terms that are referring to the masses of different types of atomic-sized particles. That's it. The terms atomic mass and atomic weight are referring to the masses of atoms. If you're referring to the mass of an atom, either a specific isotope of a certain element or one of these average values for the mass of a general atom of a specific element, then you refer to that mass as an atomic mass or an atomic weight. It's that simple. Okay, now, if you're talking about the mass of an entire molecule, like an H2O molecule or a sugar molecule or a hydrocarbon molecule, which we know you can easily determine by just adding up the masses of all of the elements contained within the molecule, well, then we're not going to refer to that mass as an atomic mass or an atomic weight. We're going to refer to that mass as a molecular mass or a molecular weight, right? It's not the atomic mass of an H2 molecule or the atomic mass of a sugar molecule. It's the molecular mass or the molecular weight of the sugar molecule. Okay, but we've talked about how at the atomic scale, if you look at any substance at the atomic scale, it's either going to be of the atom form, the molecular form, or it's going to be a lattice type structure. That's in general the three types of forms you'll see if you look at the atomic level inside of any substance. It's going to be one of those three forms. Just an atomic substance with individual independent atoms, a molecular substance, or a lattice type substance. At least in the solid state, you're going to see not individual discrete molecules, but just an infinite lattice, right? Here's pure gold. Here's NaCl. Okay, we talked about how when it comes to lattices, so with a molecular substance, the chemical formula is based on a single molecule. The chemical formula is called the molecular formula. However, with lattice substances, it's not the molecular formula, you use the empirical formula. But the empirical formula strictly corresponding to the proportions of the different atoms present or the different elements present. Because there are no individual molecules in a lattice. It's an infinite lattice. With NaCl, it would make no sense to say that the chemical formula of NaCl is Na3Cl3. Because then why not Na5Cl5 or Na12Cl12? No, you just report the empirical formula. It's one atom of nitrogen for every one atom of chlorine. But in a molecular substance, it can make sense to potentially say something like H2O2, because each molecule would contain two hydrogens and two oxygens. So you don't say HO. No, you say H2O2. But again, with a lattice substance, it doesn't make any sense to write the chemical formula as anything but the smallest ratio whole numbers of the different atoms present. You're just reporting the proportion. Okay, and so the atomic scale mass of a lattice substance is going to be calculated from its chemical formula, just like the molecular formula of a molecular substance. The molecular mass you calculate directly from the molecular formula of the molecule. H2O2, you're going to add the atomic weight of two hydrogen atoms and two oxygen atoms. With an atomic mass, or the atomic weight, it's just the mass of one of the atoms. Well, with a lattice substance, the atomic scale weight of that substance is just based on its chemical formula, the empirical formula. So NaCl, add up the atomic weight of a sodium atom and the atomic weight of a chlorine atom. And that's the atomic sized weight of the substance NaCl. For pure gold, it's just going to be the mass of a single gold atom. Okay, but the masses of these types of substances aren't called atomic masses or atomic weights or molecular masses or molecular weights. They're called formula masses or formula weights. Okay, so you see, these names are just different names for different types of atomic-sized particles. That's it. Now, so if you're determining the atomic-sized masses of any of these substances, well, at this scale, in general, we're going to be using the mass units of AMU, right, to get the masses of atoms or molecules or a lattice structure. Just based on the chemical formulas, we're just going to be adding up these atomic weights of different elements in the periodic table, right? And these are all in AMU, okay? And as we know, if you have the mass of any elementary entity, so a single atom, a single molecule, or a single unit of a lattice structure, if you have that mass in AMU, that value is also going to correspond to the molar mass of that entity, right? And so these values are also equal to the molar mass of whatever molecule you determine the mass of, or whatever atom you determine the mass of. So for a certain hydrocarbon, if you have the molecular mass or molecular weight of a certain hydrocarbon in AMU, then that value also corresponds to, if you accumulate that many grams of that molecule, then you know that you have a mole, 6.022 times 10 to the 23rd of those molecules, right? With something like NaCl, the idea is, so you have the formula mass, the formula weight, which is the weight of a sodium and chlorine atom together as a pair. Well, that also corresponds to the molar mass, meaning if you accumulate that many grams of NaCl pairs, then you know you're going to have a mole of NaCl pairs. Now, when it comes to the idea of molar mass and these average masses, these averaging of the isotope masses, all that means is, let's say you had the molecular weight of some hydrocarbon based on the averaged isotope value of the masses of all of the elements in the molecule. Well, then if you accumulate that amount of grams of that molecule, then you're going to have a mole of those molecules. So 6.022 times 10 to the 23rd of those molecules. Well, whatever the percent abundance of the different isotopes are for those elements, you just apply those percentages to the mole to get, okay, the total count of this type of isotope of this element is in that mole is going to be this. And the total count of some other isotope, you apply its percent abundance to the mole. The total count of that some other isotope within that mole of molecules is going to be this.